My name is Amita, and in this video I am going to discuss about a very important topic of in power electronics, that students face lot of problems while understanding that topic. So I am going to give a detailed discussion on that. Dear friends, inverter is a kind of power electronics converter by which you can convert a DC electrical input into a AC electrical output. As you know that the AC is available in two forms. It may be in single phase AC or a three phase AC. So accordingly, the inverters can also be classified as an single phase inverter and three phase inverter. Three phase inverter is a kind of inverter which converts a DC supply into a three phase AC supply. Three phase AC supply means it is a three phases which are apart by an angle of 120 degree. A three phase inverter operates in various modes, and in this video I am especially going to discuss about the 120 degree mode operation of an three phase inverter. If you want to see its another modes of operation, that is 180 degree mode or a 150 degree mode of operation, for that you can refer my other videos, for which a link is given in the description. So now, my dear friends, I am directly sharing my screen where I will brief you the complete detail related to a three phase inverter. So let us start with three phase inverter. Now the first thing about it is a power electronics devices based converter which is used to convert DC supply into AC supply. As the converter converts DC supply into AC supply, so the input will be DC supply and the output will be AC supply. So what I can do, DC supply, it will be the input, and with the help of inverter it converts into a AC supply which will be output. My dear friends, as you know that the AC supply is available in two forms. One is a single phase AC supply and another is a three phase AC supply. So accordingly, when inverter converts DC supply into a single phase AC supply, then it is called as a single phase inverter. And similarly, when the DC supply converts into a three phase AC supply, then it is called as a three phase inverter. Now in this video, my main focus will be on three phase inverter. So let us start with three phase inverter power circuit diagram. So the first thing that we are going to discuss, that is a three phase inverter power circuit diagram. Now let's make the power circuit diagram. So the power circuit diagram is made up of 6 SCRs and 6 diodes. Out of 6 SCRs, the 2 SCRs are connected in a single leg and they are connected back to back. So this is how the 6 SCRs are connected. This is T1, this is T4, this is T3, T5, T6 and T2. And here the input is connected with the upper plate positive and the lower plate is negative, and it's a DC kind of supply. You can see because of the DC polarity, all SCRs, all the 6 SCRs 1, 3, 5, 4, 6, 2, they will remain always forward bias, but their conduction will depend on when the firing pulse is given to which SCR. Now apart from 6 SCRs, there will be in 6 diodes, and they are connected in anti-parallel with the SCRs, so that when these SCRs are reverse biased, these diodes will provide a path for the flow of current when the SCRs are reverse biased. So there are 6 diodes which are connected in anti-parallel way, so that they can provide a path for the flow of current at the reverse bias condition of a SCRs. So from D1 to D6 there are 6 diodes, and from T1 to T6 there will be an 6 SCRs. T1, T2, T3, T4, T5, T6, these symbols I am using for the SCRs. SCRs are named as in thyristors also, and D1, D2, D3, D4, D5, D6 are the diodes. And you can see this is how the output of the 3-phase inverter is connected to the 3-phase balance load. Suppose here I am going to get the A phase output. This output is called as an B phase output, and this output is called as an C phase output. So at the middle point of a 2 SCRs connected, we connect the individual load, and this is the neutral point. Suppose this is ZA phase impedance, B phase impedance, and ZC phase impedance. It is a load connected to a ZA phase, B phase, and C phase. And I am assume load is star connected and balanced. So if it is balanced, means ZA is equal to ZB is equal to ZC, and that is equal to Z. Means the load connected to all the 3 phases, that load is having the similar value. So this is the power circuit diagram. Now when I talk, second point, when I talk about the operation, this power circuit diagram can operate in 3 modes. One is called as an 120-degree mode operation mode. Second one is called as an 180-degree mode, and third one is called as an 150-degree mode. Now in this video, I am going to brief you in detail about the 120-degree mode of operation. Now when we talk about an 120-degree mode operation, so 120-degree mode of operation. Now if I talk about this mode operation, there will be always few assumptions. Based on that, the conduction schedule of a SCR will be decided. So the first assumption number A, each SCR from the same lag. Same lag means, as you can see that in the power circuit diagram, there are 3 legs of SCR. One leg consists of, lag 1 consists of T1 and T4, lag 2 consists of T3 and T6, and lag 3 consists of T5 and T2. So the SCRs from the similar lag may be T1, T4, or T3, T6, or T5, T2. Same lag means T1, T4, or T3, T6, or T5, T2 can conduct after the duration of 180 degree. What it means, that if T1 start conducting at 0, then the next SCR from the same lag, that is T4, that can only start conducting at 180 degree. Similarly for T3, T6 and T5, T2. Now the second assumption is SCRs from same group, that is positive group or negative group. I will tell you what is the meaning of positive and negative group, can conduct at an interval of 120 degree. Now what is the meaning of this? Like if you see the power circuit diagram, if you see the SCRs T1, T3, T5, the anode of these three SCRs are at the same potential because they are short circuited and connected to the positive of a supply. Similarly, and since their anodes are at same potential and connected to the positive supply, means T1, T3, T5 can only be forward biased when they are connected to the maximum positive supply. That's why T1, T3, T5 are called as an positive group SCR. Similarly, if you see 462 number SCR, you can see the cathode of these three SCRs are at same potential. So they can be only forward biased when they are connected to the maximum negative supply. So 462 will be called as an negative group SCRs. So what are the positive group SCRs? Positive group SCRs, I can write positive group SCRs, they will be T1, T3 and T5. And what are the negative group SCRs? Negative group SCRs, why they are called negative and positive group SCRs? Because the positive group SCRs will conduct when they are connected to the maximum positive supply, and negative group SCRs will conduct when they are connected to the maximum negative supply. So as per the second assumption that SCR from the same group, that is positive or negative group, can conduct at an interval of 120 degree, means if the T1 start conducting at 0, then T3 can only start conducting at 120 and T5 can start conducting at 240. So they will be start conducting at an interval of 120 degree. And the third assumption is each SCR, as it is a 120 degree mode operation, each SCR is going to conduct for the duration of 120 degree. So now, based on these assumptions, we are supposed to make the third point, that is conduction diagram, or it is also called as an schedule, conduction schedule of the SCRs. So that diagram I can make in form of block. So what we are supposed to do, we are supposed to draw the three parallel lines. Suppose this first is showing the lag 1, that is T1, T4. This is lag 1, which consists of T1, T4. Second row is showing lag 2, which consists of T3, T6. And third one is lag 3, which is T5, T2. And suppose this is 0 and at last it is 360. So we are drawing it only for one complete cycle. This is also 0 and this is also 0. Let me draw with another color so that you can understand. I'm drawing it with red color. So suppose this is 0, this is 0, this is 0. If T1 start conducting at 0, then as per the rule number 1 or assumption number 1, the T4, which is the SCR from the same group, same lag, can only start conducting at 180 degree. So 0 to 180 T1 will conduct and 180 to 360 T4 will be conducting or forward bias duration. Similarly, as per the second assumption, the SCR from the same group, so T1, T3 and T5, they are from the same group. So SCR from the same group, they will start conducting at an interval of 120. So if T1 start conducting at 0, then the SCR from the same group, that is T3, that will also start conducting at 120 degree. And next SCR from this, that is T6. T6 means T6, if T3 start conducting at 120, then as per the assumption number 1, T6 can only start conducting at 300. So T6 can start conducting at 300 and here also T6. Now similarly, the next SCR from the positive group, that is T5. So T5 start conducting at a delay of 120. That means T5 start conducting at 240 and it will be forward bias for a duration of next 180. So 240 may if I add 180, what I am going to get? That is 60. So up to 60, T5 will be forward bias, and from 60 to 240, T2 will be forward bias. Now, as it is a 120-degree mode, so as per the third assumption, each SCR can conduct only for a duration of 120. So if T1 starts conducting at 0, then it will be only conducting up to 120. So that means from 120 to 180, there will be a duration when no SCR from the lag 1 is conducting. T4, if it is start conducting at 180, so it will be conducting only 300 because it is a 120-degree duration, and 300 to 360 will be the duration when no SCR is conducting. Similarly, if T3 start conducting at 120, then it will conduct only for a duration of 120, so means it will conduct up to 240, and 240 to 300 will be the duration when no SCR is conducting. T6 start conducting at 300, so 300 may if I add 120, it will go up to 60. That means T6 will be conducting only up to 60, and 60 to 120 will be the duration when no SCR is conducting. At last, if I see the lag 3, T5 if it starts conducting at 240, if I add 120 in this, that is up to 360. That means T5 will be conducting up to 360, and 360 means 0. So 0 to 60 will be the duration when no SCR is conducting. At last, if T2 start conducting at 60, if I add 120 in that, that means T2 will be conducting up to 180, and 180 to 240 will be the duration when no SCR is conducting. So this is the conduction diagram of an SCRs in the power circuit diagram. Based on the conduction diagram, now we will make the conduction table. So what we are supposed to do, we will write the duration. Here in the duration, we will write the duration between 0 to 360 at an interval of 30. So then the next thing is conducting SCR. Then we are going to write VAN, VBN and VCN. So they are nothing but they are the phase voltages. So we are going to calculate the phase voltages, and at last we are going to calculate the line voltages VAB, VBC and VCA, and they are nothing but they are the line voltages. So conducting SCRs for a particular duration, we are going to calculate the phase voltages and line voltages across the load. So first, let us start the duration at an interval of 30 up to 360. So 0 to 30, then 30 to 60, then 60 to 90, then 90 to 120, then 120 to 150, 150 to 180, and 180 to 210, then 210 to 240, 240 to 270, then 270 to 300, 300 to 330, and at last 330 to 360. So what we have done, we have written a duration for a one complete cycle, that is 0 to 360 at an interval of 30. Now to determine the conducting SCRs, that we can determine with the help of conduction table. You can see that 0 to 30, which SCRs are conducting? T1 and T6. So what we are going to write? The conducting SCRs are T1 and T6. 30 to 60 also T1 and T6. But if we see 60 to 90, that is T1 and T2. So depending on the conduction diagram, we are supposed to write the conducting SCR. So 60 to 90 will be T1, T2, T1, T2, then T2, T3, then T2, T3, then T3, T4. So we will get, if you see the conduction diagram, we will get such kind of conducting SCR sequence. So again T3, T4, then T4, T5, again T4, T5, then T5, T6, and at last T5, T6. So if we see these conducting SCRs, you can observe that for two duration like 0 to 30, 30 to 60, T1, T6 are conducting. That means at every 60 degree, the conducting SCRs is changing. And after an interval of 60, the one SCR will be the incoming and another SCR will be the outgoing. Like 30 to 0 to 60, T1, T6 are conducting. But once you move to the next duration, that is 60 to 90, you can see that T6 is outgoing SCR and T2 is incoming SCR. So at an interval of 60, at every 60 degree interval, you will observe that one SCR will be the outgoing SCR and another SCR will be the incoming SCR. Now, depending on the conducting SCRs, if I draw the equivalent power circuit diagram, so what I will do, equivalent, to determine the phase voltages and line voltages, I have to draw the equivalent circuit diagram. Okay, so let us draw the equivalent circuit diagram between 0 to 60 duration. What are the conducting SCR in this? That is T1 and T6. So for this duration, if I make the equivalent circuit, what will be the equivalent circuit? T1 is conducting, so it will be act as a short circuit. T4 is not conducting, so it will be open circuit. T3 is also not conducting, so open circuit. T6 is conducting, so it will be short circuit. And similarly, T5 will be open circuit and T2 will also be open circuit. So this will be the behavior of the conducting SCRs, and based on that the equivalent circuit will be like this. So when I connect the load, three-phase load which is star connected, that will be like this. So this is Z, this is A phase, this is B phase, this is C phase. So this is a three-phase star connected load where the impedance for A phase is ZA, impedance for B phase is ZB, and impedance for C phase is ZC. Now, as I have assumed that the load is balanced load, you can assume that ZA is equal to ZB is equal to ZC is equal to Z. So now if we redraw the circuit, after redraw the circuit, you can see that ZA impedance, which is equal to Z, through this T1 is connected to plus of Vs. So let me draw ZA impedance with the help of T1 short circuit is connected to Vs, and this is A phase. Similarly, the B phase through this T6 short circuit is connected to the negative of the supply. So this is ZB and this is V, this is Vs, and this is point neutral. You can see that the C phase is not connected to supply because neither the T4 is short circuit nor T2 is short circuit. Now if for the balanced load ZA and ZB is equal to Z. Now if I going to calculate VAN and VNB, you know that if a single voltage source is connected to the two series impedances, then the voltage across the individual impedances we can calculate by voltage division formula. So what is voltage division formula? The voltage division formula is that voltage across ZA will be equal to the supply voltage multiplied by the impedance ZA, that is equal to Z, divided by the addition of two impedances which are series connected. So by applying the voltage division formula, I can get Vs ZA upon ZA plus ZB. Now since it is a balanced load, so Z upon 2 into Z. So what I am going to get? Vs by 2. Similarly, VNB also Vs ZB upon ZA plus ZB. So again for a balanced load, Vs upon Z upon 2Z. So the VNB also is equal to Vs by 2. But my interest is to calculate VBN, and VBN is equal to minus of VNB. So this is equal to minus Vs by 2. So what we have calculated? VAN is equal to Vs by 2. VBN is equal to minus Vs by 2. So the value calculated is, it is Vs by 2. VBN is minus Vs by 2. And the value of VCN is 0. Now as for 30 to 60, same SCRs are conducting. So the value is going to repeat, that is 0. Now again, if the T1 and T2 are conducting, again 60 to 90 duration, again the second thing is 60 to 120 duration. What are the SCRs conducting? T1 and T2. So when T1, T2 are conducting, what will be the equivalent circuit? T1 will be short circuit, T4 will be open circuit, and T3 will be open circuit, T6 will be open circuit, and T5 will be open circuit, and T2 will be short circuit. So this will be the conducting SCR between 60 to 120. Now when I connect the load, that will be connected like this. This is ZA, star connected load. This is ZB, and here there is a ZC. So all three loads are connected in star, and this is neutral, this is A phase, this is B phase, this is C phase. Now if I redraw its circuit, that will be like this. You can see that ZA impedance through the short circuit of T1 is connected to the positive of a supply. So this is A phase, and the ZC is connected through T2 short circuit to the negative of supply. So that will be like this. So this is Vs and this is V. Now if I am going to calculate the voltage across ZA, that is VAN, that is by voltage division formula, that is Vs into ZA upon ZA plus ZC. Now for balanced load, here I can write voltage division formula. Now for a balanced load, what is my VAN? That is balanced load के लिए ZA is equal to ZB is equal to ZC, and that is equal to Z. So what I am going to get? Vs is equal to Z upon 2Z. So I am going to get Vs by 2. Now similarly, this is not B, this is C. Now similarly, VNC will be equal to Vs ZC upon ZA plus ZC. Now if I calculate it for balanced load, that is Vs bar Vs into Z upon 2Z. So what I am going to get? VNC that I am going to get, that is Vs by 2. But my interest is in VCN, so that is minus Vs by 2. So what is VAN? VAN is Vs by 2, VBN is 0, and VCN will be minus Vs by 2. So what I can write? Now when T1, T2 are conducting, what is the value I am getting? Vs by 2, 0, and minus Vs by 2. Then again Vs by 2, 0, minus Vs by 2. So this is how we are going to get. Now when T2, T3 are conducting, when T2, now let us calculate for the next duration when T2 and T3 are conducting. So that is from 120 to 180. So when we are going to calculate for C, we are going to calculate for, now the C part, 120 to 180 duration, which SCRs are conducting? T2 and T3. So if I draw the equivalent circuit, T1 will be open circuit, T4 will be open circuit, T3 is now short circuit, 6 is open circuit, T5 is open circuit, and T2 is short circuit. So this will be the circuit and it is connected to the DC supply of Vs voltage. Now if I see the connected load across A, so this will be ZA, this will be ZB, and here it will be ZC, and they are connected star like this. Now this is A phase, this is B phase, this is C phase. So depending on the conducting SCR, if I redraw the circuit, you can see that the B phase through T3 short circuit is connected to the positive of the load. So this is ZB and it is connected to the positive, and this is B phase. Similarly, through the short circuit of T2, the ZC is connected to the negative of the supply. So ZC will be connected negative to the supply, and this is C, this is Vs. Now again, by voltage division formula, by voltage division, what I am going to get? VBN is equal to Vs ZB upon ZB plus ZC. Now for balanced load, ZA is equal to ZB is equal to ZC is equal to Z. So what I am going to get? VBN is equal to Vs upon Z upon 2Z. So that means Vs by 2. Now similarly, I can calculate VCN, that is equal to minus Vs by 2. So let us write in the table, VBN is Vs by 2 and VBC is VCN is equal to minus Vs by 2. So VAN in this case 0, VBN is Vs by 2, and this is minus Vs by 2 and minus Vs by 2. Now similarly, if I calculate here for next duration, minus Vs by 2, this will be Vs by 2, this will be Vs, this will be 0, sorry. So this will be 0, 0. Now again, this will be minus Vs by 2, this will be 0, 0, this will be Vs by 2, then 0, 0, this will be minus Vs by 2, this will be Vs by 2 and Vs by 2. So this will be your table, conducting SCR's table. Now, as I have written here, we have calculated the phase voltages. Now, to calculate the line voltage, what is VAB? VAB is nothing but VAN minus VBN. So if I subtract this from this, what I am going to get? Vs by 2 minus of minus Vs by 2. So means Vs. Now here I am going to get Vs by 2. Then Vs by 2. Then minus Vs by 2. This is how we are supposed to write. So this is again minus Vs by 2. This is minus Vs. This is minus Vs. This is minus Vs by 2. Then here also minus Vs by 2. Then Vs by 2. Then Vs by 2. So this is how we are going to calculate VAB by subtracting VBN from VAN. Now the next is VBC. So VBC means VBN minus VCN. So that is minus Vs by 2. This is also minus Vs by 2. This is Vs by 2. This is Vs by 2. It is Vs. This is Vs. Then Vs by 2. Then Vs by 2. Next is minus Vs by 2. Then minus Vs by 2. Then minus Vs. Then minus Vs. This is how we are going to calculate VBC. Now at last VCA will be VCN minus VAN. So that will be minus V was by 2. Then minus Vs by 2. VCN matlab VCN minus VAN. Now what is this? Minus Vs minus Vs minus Vs by 2. Then minus Vs by 2. Then Vs by 2. Vs by 2. Then Vs by 2. Vs 2. So this is how we will get the line voltage. Now you can see here that the phase voltage is VAN. 4 times we are getting Vs by 2, then 0. Then 4 times we are getting minus Vs by 2, then 2 times 0. So let's draw these waveforms. So let us draw the waveforms. So now the fifth part is phase voltages waveform. Phase voltages waveforms means VAN, VBN and VCN. We are going to plot these waves. Now for that I am supposed to make the y-axis, and then the next line is like this, and third line, that is for VCN. So here I am going to plot VAN, this is VBN and this is VCN. Now this is, let me draw with a different color. This is 0. So let us write 0, 30, 60, 90, 120, 150, 180, 210, 240, 270, 300, 330. So this is how we need to extend the time. Dear friends, I am making these waveforms freehand, but when you are going to make, you are supposed to make with the help of proper scale. Now you know, I will make VAN by green color, VBN I will make by white color, and for VCN I will use yellow. So VBN is green, so let's select the green color. Now we know 0 to 6, 0 से लेके 4 duration तक I am going to get Vs by 2. Now 122 next to duration I am getting 0. Then for 4 duration, that is up to 300, I am getting minus Vs by 2, and then again 0. So what is this value? What is this value? Vs by 2. This value 0, and this value is minus Vs by 2, and again it is. Now the next is, this is for VAN. Now the next is VBN. So VBN, if you see VBN 120, if you see the conduction table 120 to 240, we are getting Vs by 2, and 240 to 300 we are getting 0, and then again minus Vs by 2, and here also minus Vs by 2 up to 60, and then from 60 to 120 it will be 0. So this is the waveform for VBN. Now if I see VCN from the conduction table, the waveform for the VCN is from 240, its value is Vs by 2. So 240 to 360 Vs by 2. Then 0 to 60 it is 0. Then it is having minus Vs by 2, and then it is value is 0. So Vs by 2, 0, 0 and minus Vs by 2. Now you can see here that Van is having Vs by 2 at 0. But if you see the waveform of Vbn, the waveform will repeat after 120 degree. If you see Vcn, the same value of Vs by 2 is coming at 240. So with the help of these waveforms, we can see that Van, Vbn and Vcn are apart by an angle of 120. And this is what a three-phase AC supply. So it means that we are going to get a three-phase AC voltages. Now, if I draw the next thing, that is the line voltages. If I draw the next thing, that is three-phase line voltages. That is VAB, VBC, VCA. So again, I am supposed to draw the y-axis, then this is x-axis, one x-axis for VAB, this is for VBC and this is for VCA. So here I am going to plot VAB, here I am going to plot VBC and here I am going to plot VCA. Now let us write the duration that I will do with the help of red color. So what I am going to write, this is 0, this is 30, this is 60, this is 90, this is 120, this is 150, this is 180, this is 210, this is 240, this is 270, this is 300, this is 330 and so at last this is 360. Now let us extend these instants so that the instant of all the three line voltages should match and we can see the phase displacement. So let us draw these waveforms. Dear friends, when you make these waveforms with a proper scale or on a graph paper, that will be exactly with the same dimension. Here I am drawing the waveforms with freehand. So we have extended up to 360. Now my dear friends, VAB I will plot with green color. VBC, just to show the difference, I will plot with white color. And VCA I will plot with yellow. So now if you see the conduction table, let's see, VAB, I am getting Vs, 2 times Vs, 2 times Vs by 2, then minus Vs by 2. So it is starting from Vs, Vs by 2, minus Vs by 2, then minus Vs. So like Vs, Vs by 2, minus Vs by 2, then minus Vs, then 2 times minus Vs, Vs by 2. So how it is going? Vs, Vs by 2, minus Vs by 2, minus Vs, minus Vs by 2 and then Vs by 2. So how we are supposed to draw the line voltages? VAB is starting from, let's have a green color, little bit thicker line. So you can see it is starting from Vs. So the value is Vs. And then from 60 to 120, it is Vs by 2. Then 120 to 180, it is minus Vs by 2. And then 180 to 240, it will be minus Vs. And then 240 to 300, it will be minus Vs by 2. And then it will be Vs plus Vs by 2 up to 360. So this is how I am getting the waveform for a VAB. Now let us draw the waveform for VBC. So when I plot the waveform for VBC, it will start from minus Vs by 2. So when I plot the waveform for VBC, VC. So VBC will have an VS value at 120 to 180, then Vs by 2, then minus Vs by 2, then minus Vs, and here minus Vs by 2, and then plus Vs by 2. So this is the waveform for a VBC. Now at last, if I plot the waveform for VCA, so VCA means it is having the value of Vs for this duration 240. So Vs, then it is having the value of Vs by 2, then it is having the value for this duration minus Vs by 2, then plus Vs by 2, minus Vs by 2, and then it is having Vs by 2. Vs by 2 के बाद it is having minus Vs, then minus Vs by 2, and then it will be having a value of Vs by 2. So this is how we will get the waveform for VCA. Now if you observe these three line voltages, the value of VAB at 0, that is Vs. And if you see the waveform for VBC, this plus Vs is starting at 120, and for the same VCA, the value is starting at 240. So the waveform of VBC and the VCA is delayed by an angle of 120 degree. Like VBC is delayed by an angle of, is lagging from VAB by 120, and VCA is lagging VBC by 120. So that means VAB, VBC and VCA are displaced by an angle of 120 degree, and that is three-phase AC line voltages. So this is how we can get the three-phase AC line voltages also. If you see the line voltages, how many labels we are having? One label is Vs, another is Vs by 2, third is minus Vs by 2, and fourth is minus Vs. So that means line voltages mein how many labels we are getting? Line voltages of a three-phase inverter, line voltages of three-phase inverter 120 degree mode is having 4 label output. Whereas if I see the phase voltages waveform, we are getting Vs by 2, 0 and minus Vs by 2. So we can conclude that the phase voltages waveforms are having 3 labels only. So my dear friends, I hope I have cleared each and everything related to an three-phase AC inverter. You can observe the voltages waveform, phase voltages and line voltages. Phase voltage waveform, we are getting 3 label. Line voltages waveforms, we are getting 4 label. And you can see we are getting the alternating cycle. Like if I explain the phase A to neutral voltage waveform, you can see that we are getting positive and negative cycle as well. Although it's not a pure sinusoidal waveform, these are also called as a quasi-square waveform inverters, because in place of a pure sinusoidal waveform as an output, we are getting the stepped output. And after filtering this step output, we can convert these quasi-square waveforms into the form of pure sinusoidal waveform. My dear friends, I hope whatever information I have shared in this video related to a three-phase inverter 120 degree mode operation will be clear to you. If you want to see 180 degree mode operation, kindly refer the link which I have mentioned in the description. And for 150 degree mode operation, kindly watch my next video. My dear friends, I just want to tell you that if in case of three-phase inverter, if we will get the output in a more number of steps, the waveform will be more closer to the sinusoidal waveforms. Like in 120-degree mode operation, we have seen that in phase voltages, we were getting the 3 label output voltage waveform, and if we see the line voltages, that will be the 4-step output voltage. Similarly, in next video, I'm going to discuss about the 150-degree mode operation. When you go for in 150-degree mode operation, the waveform will be having more steps in the output. That means the output waveform will be more closer to the sinusoidal, and it will have a less number of harmonics. My dear friends, if you like this video, kindly press the like button. And if you feel that whenever I make such kind of videos, a notification should reach to you, then don't forget to subscribe my channel.